This morning, Dr. Cox presented Aylmer's observation on the evolution of material in the interstellar medium into the protoplanet disk. So my work is connecting to that point. So I'm here to present the devolatilization from a star to its rocky planet, which I have been collaborating with Charlie Lineweaver, Trevor Ireland, and Fan Liu at Australian National University. So the idea of this research is straightforward. So we can envisage that the complex process of forming rocky planets are essentially a process of losing volatiles. So that, based on that, so from the protosun and the Earth, and if we plot the abundance ratio as a function of condensation temperature, and starting with the protosolar abundances, and we could see for refractory elements, their abundances are essentially identical between the terrestrial planet and the protosun. While for moderately volatiles, they will be depleted in the Earth relevant to the protosun. So this idea is similar to the previous studies of volatility trends. For example, Kage-Lewis in 1993, as well as the more recent work. However, these previous studies has no uncertainties associated with the bulk composition. So without the uncertainties, that will limit us to do the quantification of this trend to be useful for representing the chemical relationship between a star and its planet. So we have been firstly dedicated to exploring the uncertainties on the bunkers composition, and then to replace Ci chondritic abundances by the solar nebula abundances. Well, for the bunkers composition, we compile and combined from a large set of heterogeneous compositional estimates for the primitive mantle and the core. And in using new estimates of core mass fraction, and we construct, that is constrained from the seismological and astronomical constraints. So we construct the bulk Earth composition with uncertainties. And this comparison with the previous determinations, and we believe our estimate has been usefully calibrated our current best knowledge of the bulk Earth composition based on various models. So now is, okay, what's the protosolar abundances, as I just talked about? So this diagram shows the comparison between the Ci chondritic abundance in the x-axis and the solar photospheric abundance in the y-axis. And everything along this line, they are essentially identical between the Ci contrast and the photosphere. And for the elements above the line, such as noble gases, hydrogen, carbon, nitrogen, they are depleted in Ci contrast, but well determinable for the solar photosphere. And for the elements below this line, such as lithium, it's depleted in the photosphere, and but well preserved in the primitive meteorites. And for the elements along these lines, they have no photospheric lines, so that we have no photospheric abundances. So based on this complementarity of abundances between Ci contrast and solar photosphere, we construct our protosolar abundances based on the latest estimates for the photospheric and Ci chondritic abundances. And from the lower pattern, we can see the variation of our estimated protosolar abundances as the yellow pattern, and in comparison with the derived data. Well, now we have had our best estimates for the planet Earth and the protosun, then we can plot them together and to show, okay, we can investigate their possible conversational relation. And for example, from the zoom-in part, these refractory elements, their abundances are essentially identical between the terrestrial planet and the protosun. But for the green dot shows the moderately volatiles, they are depleted in the terrestrial planet relevant to the sun, and their depletion scale is increasing versus the decrease of the elemental condensation temperature, Tc. While for these highly volatiles, they are highly depleted in the terrestrial planet and scattered around in the lower region of the Tc. Then we replot these abundance ratios in a log scale because that can give us more obvious, well-constrained trend for this element. So we fit a joint model to the abundance ratios versus the TC, and that led to our devolatilization pattern for the Sun to the Earth. And this also determines a critical devolatilization temperature, and that divides the depletion and non-depletion elements of the terrestrial planet relative to the Sun. And we also interpret the temperature as plausibly the highest temperature that has been experienced by the material in the feeding zone of the Earth, proto-Earth, during the formation stage. And the lower two panels show the OC and the cumulative chi-square for the best fit. Well, now we may ask a question. Is the Sun to Earth devolatilization pattern really represented enough for the depletion features of solar system rocky bodies? So the answer would be yes and no. And why we say that? So because this reason includes twofold. On the first hand, if we compare the planet Earth and a CM group of contrasts in the green dots and a CM contrast at the red dots, and we do see this systematic difference of elemental depletion between these rocky bodies. However, if we focus on the terrestrial planet zone, and in terms of Mars, Venus, and Earth, their depletion features, their differences are really indistinguishable. But based on this current data we could have for the Mars and Venus. And so that's intensely tell us that the Sun to Earth devolatilization pattern is still fair enough to represent the first order devolatilization from the proto-Sun to the terrestrial planet, including this variation. So why this matters? So this is relevant to the theoretical modeling of exoplanetary interiors, including chemistry and structure. And to do that, we need two sets of information: planetary mass and radius, and the host stellar abundances. And here I focus on the host stellar abundances, because this has been overwhelmingly popular in the prevalent exoplanetary interior model. For example, the keywords as shown here: from stellar chemistry, using stellar abundance proxies, using stellar composition, and from stellar abundances. However, based on our knowledge of the solar system, we know for sure the planetary boundary composition is not identical to host stellar abundances, especially for non-refractory elements. So this could be also true for the major rock forming elements like iron, nickel, silicon, and magnesium. That depletion is about 10 to 20%. But for carbon, sulfur, and oxygen, these moderately or highly volatile. And this depletion can up to 3 orders of magnitude. That would definitely have a profound impact on the interior mineralogy of such exoplanet if we apply this procedure. So we made a test in the case of a well-known planet host, Kepler-10, and we refer to two sets of host stellar abundances. One is with larger uncertainties, as shown as K10, and the other is more precisely determined, as shown K10 star. And then we applying this devolatilization algorithm to the host stellar abundance that will lead to the possible elemental composition of the rocky exoplanet in the circumstellar habitable zone of the star. And as shown is the K10XOE and K10XOE star. So even in the case of the iron to silicon that are slightly depleted, but we still can see this significant difference between the star and the planet, especially for the more precisely determined abundances. And for carbon and oxygen, this difference is more profound. It's about 1.7 dex, that is about 3 orders of magnitude. So this will have profound impact to the interior mineralogy calculation and even structure as well as habitability analysis for these rocky exoplanets. So we made a more test. This is my last slide. So based on this devolatilization algorithm, and we, based on the assumption for the initial chemical system for the mantle and the core, we can compute the mantle and the core composition as well as the core mass fraction, and for these selected cases. And as a verification, we also apply this procedure to the protosun, and we model the elemental composition of the model Earth. And then it's amazingly these results for mantle and the core composition, including the core mass fraction, are consistent with the totally independent determination from the parallel acidic Earth and other determinations. So this essentially gives me a sense that from the star to its orbiting planet, the devolatilization matters. And the Earth to the Sun devolatilization pattern can be served as the first-order chemical relationship between a star and its rocky planet. And applying a devolatilization algorithm to the host stellar abundances can substantially help reduce the current degeneracies in the estimates of interior structure and mineralogy and even habitability of rocky exoplanets. Thank you.